it would be greatly benefit all our participants because they want to learn regarding hardware security and how they apply it to IoT part. So before we request Professor Sengupta, and I'll ask Ayaskan to introduce Professor Sengupta formally, and then we'll go ahead with the lectures.
Okay,
so Ayaskan, please take.
Thank you, sir. Sir, can I request Anirban, sir, can you please switch on your camera if possible for some time?
Yeah, thank you so much, Professor Mahapatra and Professor Swain. So it's an honor for me to be part of this FDP. However, the only problem is I'm attending through my desktop, so I don't have a webcam, unfortunately.
Okay. Thank you, sir.
So yeah.
Okay, thank you, sir.
I hope that's not an issue.
I feel honored to introduce our today's speaker, Dr. Anirban Sengupta. Dr. Anirban Sengupta is an associate professor in the discipline of computer science and engineering at IIT Indore. He has more than 260 publications, including 11 patents and 4 books. He is recipient of awards, honors such as Fellow of IT, Fellow of British Computer Society, Fellow of ITE, IEEE Chester Saul Memorial Consumer Electronics Award, IEEE Distinguished Lecture, IEEE Distinguished Visitor, IEEE C Society, IEEE CS Outstanding Editor Award, IEEE C Society Best Research Award from CEM, and IEEE TC VLSI Best Paper Award. He occupied more than 17 editorial positions in IEEE or IET journals. He is ranked in world's top 2% influential scientists by Stanford University 2022-2021, ranked in world's top 0.3% scientists by Stanford University in the domain of computer hardware, information technology, or networking and telecommunications in 2022-21, featured in top 10 Indian scientists in computer hardware and architecture field, and in top 16 Indian scientists in networking and telecommunication field from the list of world's top 0.3% scientists by Stanford University. I request, sir has already shared his PPT, so I request sir to start his talk.
Okay, thank you very much for the kind introduction. Once again, I'm honored and grateful to NIT-Rourkela and Professor Mahapatra and Dr. Swain and the others who have been part of this FDP in inviting me for this talk. So I will generally speak about hardware security, and at times I will emphasize on IoT and consumer electronics and cyber physical systems and things like that. Because hardware security is a broad topic, and that actually encompasses and covers up most of these classified fields that we are using these days. Okay. So since I'm assuming that we have an audience comprising of people who have been working in this domain as well as people who are new, so I will start from the basics of the area, and gradually I will move into some of the critical problems that have been solved by us in our research lab as well as others across the globe who has been making an effort in solving similar problems. So what are the topics we are touching upon today or covering? So of course there are a lot of things we are touching upon, and I really understand that it may not be really feasible for all of you to really understand each of these in depth. However, I'll try my best to give you the basic overview of each of these topics. I will also talk about some of the recommended books, because I believe that the books that I have written, which have been consecutively published in the last 4-5 years in IET, they actually cover most of the important topics on hardware security. So I will encourage you to have them in your library if possible. Otherwise, you can read them online as well. So, and I will keep on touching about the other major branches of hardware cyber security. I would like to use the word cyber security because it is actually, hardware security is actually part of the security of cyberspace and cyber systems. So we call that as hardware cybersecurity, to be more precise. And that actually involves a lot of things like IPP, which we call as IP core protection of different devices. Okay, that ranges from basic combinational circuits, sequential circuits, to some higher end, systems such as hardware accelerators, application-specific processors, application-specific integrated circuits, and so on and so forth. So we'll give examples of that. Also, we have made some very prominent efforts in the domain of developing security CAD tools that are currently hosted under IEEE, Security Committee, as well as IEEE Council on Electronic Design Automation at University of Florida Cybersecurity Research Center. So these are publicly available. So any researcher, any student, any faculty, or people working in industry can actually have a look at that and can use them. So far we have received very good response from the different, industry and academic community in terms of download and viewing those tools. And it has actually exceeded more than 4,000 downloads so far. And we'll also cover other topics like steganography, watermarking, obfuscation, encryption, so on and so forth. So these are the top 3 books that I would recommend you to have a look at them, because they actually cover the basic concepts related to hardware security. They also cover topics related to digital intellectual property code security. They talk about security of DSP processors, image processing processors, and so on and so forth. Fine. So now let's get into the technical side of the talk. So for people who are very new, the very first question that comes to the mind is, what is hardware security? So I would like to extend the name as hardware security and intellectual property core protection. We call that, in short, IPP. It is an emerging area of research, although now a lot of research has already happened in the last 10 years, and specifically, from some selected research groups across the planet. But still, there's a lot of scope that is there that we can do things on that. So it focuses on the protection against standard threats such as reverse engineering, counterfeiting, forgery, malicious hardware modification, as well as something known as fraudulent claim of IP ownership. So we therefore classify hardware security into 2 types. The first is called the authentication-based approaches, and second is obfuscation-based approaches. The authentication-based approaches are the ones which deal with the threat model of trying to safeguard your IP ownership, as well as providing sturdy and robust detection against pirated hardwares. Okay. And the obfuscation-based approaches, since it's more classified, so it can be again subdivided into 2 types. The first is called structural obfuscation, and second is called functional obfuscation. Structural obfuscation transforms a design into a version that is functionally equivalent to the original design. However, is more difficult to reverse engineer. Okay, so we will have to think of ways how we can structurally obfuscate a design such that it doesn't affect the end functionality. It is a kind of passive mode of protection, and the second one is called functional obfuscation or logic encryption. It actually deals with protecting the design netlist in such a way that it remains protected until you apply the right predefined sequence of secret key into the design netlist. Now let us have a look at the SoC lifecycle or the VLSI design abstraction levels that are part of protecting the hardware. So in a typical SoC lifecycle, you have an IP vendor, the SoC design house, the foundry, and the deployment stage. Each of these stages have its own set of negative threat models that can be vulnerable for an intruder to insert different type of hardware threats and different types of malicious logic into the design. So IP vendor is a stage where insertion of hardware Trojan is possible because it acts as a hidden backdoor entry. So the solution is to have something known as Trojan resistant design, such that you can improve the detectability and you can have more trust on the validation phase. In the SoC design house, there is a possibility of IP piracy. So the IP vendor should be careful and should have ways or provisions in mechanism. In the foundry stage, there is a possibility of things like Trojan in the design, where implantation can be made because foundry is an untrustworthy regime or site where a lot of Trojan infections are possible. There is also possibility of overproduction and cloning there. So a lot of mechanisms such as hardware obfuscation, POF, low-cost authentication can be deployed to take care of that. And in the deployment stage, there is a possibility of leakage of secret information, reverse engineering and cloning, where you need designs such as SCA resistant, scan-based attack, variable ECC, and so on and so forth. Now, again, if you look into the cycle in a more detailed way, what I've done here basically is at different stages, I've actually highlighted the trust issues that exist. So in the IP acquisition stage, Trojan attacks are possible. And in the SoC integration phase, IP piracy, Trojan attacks and extraction of design secret information is possible. In the IC fabrication stage, Trojan attacks are possible, overproduction is possible, reverse engineering is possible. And finally, as you move on into the deployment stage, you have things like side channel attacks, fault injection attacks, and so on and so forth. So this entire cycle is part of the CAD4 assurance of electronic systems. So it is a widely known and widely acknowledged, diagram that is used by several research groups to understand the threat model. Now moving on, what I would like to emphasize here is that for people who want to work in the field of hardware security, even if they want to start, they must have the basics of VLSI to move on into this area. If somebody doesn't have the background of VLSI or digital system design or even computer architecture, it becomes slightly difficult to advance into this field. Because when you talk of hardware security, you must understand what type of hardware. There are different types of hardware, and not all type of hardware are actually designed in the same way. For some hardware, we design from the RTL stage. For some hardware, we design from the gate level, design stage. For some, we need to move up in the abstraction layer and start from the architecture level. So different hardware has their own requirement, and therefore we need to understand which level of abstraction we need to exploit in order to embed the security algorithm and embed the security protocols. So I will focus more on something known as hardware accelerators, because this is something which my group and I have been working on in the last 10 years. And they are actually the high-end applications of combinational and sequential circuits. So let us have a look at what are hardware accelerators first. So hardware accelerators are basically the reusable intellectual property cores or application-specific processors that are used for digital signal processing and image processing applications. Some examples could be finite impulse response filter, FIR, JPEG codecs, convolution filter, which can again have different types such as blurring filter, image sharpening, image embossing, image detection, so on. Then you have discrete Fourier transform, DFT. Then you have DCD, discrete cosine transform, so on and so forth. There are different types. So these applications, the ones which I've referred here, they actually serve as the benchmark applications on which you need to test your security algorithms. So when I mean testing, you need to employ your security algorithm as well as design a secured hardware that utilizes and exploits your security algorithm. That's how you can actually make a prototype and validate whether your security algorithm works or not. Now, different types of security techniques have been proposed by us as well as from the other groups, but of course we have been predominantly working on hardware accelerators and these sort of applications more. So we have in the recent past. Of course, I have put here only the most 5 prominent, technologies that we have produced, and some of them are currently in the commercialization stage, and some of them have already been commercialized. So these are the 5 most prominent, algorithms converted into secured CAD tools. So first is based on cryptosteganography. I'll talk about what steganography means. The second is integrated watermarking and key-based structural obfuscation. Third is on biometrics, so that exploits fingerprint, facial, palm print, retina, and different other human features. Then we have integrated cryptosteganography and structural obfuscation. And finally, we have something known as key-based hash chaining. So these are the most prominent ones that have been published and deployed so far. Now, when we talk of IP core protection, which I said is a very important sub-branch of hardware security, we need to understand what is the main function of IPP. So IPP is basically used for forensic detective control of pirated designs. So before the pirated versions get integrated in the SoC design house and gets further manufactured as a consumer electronic system, it needs to be validated and authenticated. It needs to be ensured that we do not integrate a pirated version of the IP into our system. Okay, so there needs to be proper mechanism in place to ensure detective control so that it can act as an isolation mechanism. So what are the ways? So again, watermarking has been identified as one of the most important ways, because watermarking of images and multimedia data has been widely known for several years. So watermarking of hardware can play a vital role. So different research papers and patents have been produced in various prestigious journals. So some of them are single phase hardware watermarking, multi-phase hardware watermarking, multi-level hardware watermarking, hardware steganography, as well as something known as digital signature based watermarking. Now looking into the other dimension of hardware security, which is trying to handle threat of reverse engineering or malicious alteration of RTL design. So usually obfuscation is employed. So obfuscation is a way to actually make your design transform into a form that is unobvious to an attacker or uninterpretable to an attacker. You don't want your design to be easily decoded. You don't want your design to be easily, decamouflaged. So you are trying to make your design look uninterpretable and obvious, so that an attacker cannot really identify the actual functionality and the details of the interconnectivity, so that he can find safe locations in the design to hide his malicious logic. And also, if he cannot really identify the exact functionality and the interconnectivity, it would act as a deterrent for piracy. So obfuscation is a multitude angle here. So what are the different obfuscation techniques? So first of all, compiler transformation based structural obfuscation of DSP circuits have been proposed, and high level transformation of structurally obfuscated fault secure DSP circuits have also been proposed. So by fault secure DSP circuits, I meant transient fault secure DSP circuits, that is the DSP circuits that are prone to radiation induced faults. The third is hologram based structural obfuscation, and finally we have something called functional obfuscation of DSP circuits using logic locking or logic encryption. So where you apply a combination of different encryption mechanisms and locking gates in order to block an attacker from decoding it. And the fifth category is functional obfuscation of DSP circuits that uses logic blocks as well as advanced encryption standard, ciphers, SHA, and other lightweight solutions in order to guard it against threats such as key sensitization attacks, SAT attacks, and removal attacks. So we'll also talk about those attacks today in short. Now let me come to the core of the phase where the security framework actually works. So we need to understand what is high level synthesis, because if you think about the abstraction levels, you know that there is an architecture level, that there is an RTL, then we go to gate, then we go to layout, and so on. Now, high-level synthesis actually works in the phase between architecture level and RTL. Okay, so that's an important phase to capture, because if you're able to exploit and capture that phase, so you can integrate your security framework there. So most of the approaches that have actually handled the security of complex designs, such as these hardware accelerators, reusable IP cores, ASICs, and so on, they actually try to exploit the HLS, which is high-level synthesis. So what is high-level synthesis? It's a mechanism that captures the algorithmic level behavior of such hardware accelerators and converts it into its register transfer level counterpart. Okay, and it includes several important phases such as DSE, which is known as design space exploration, scheduling, hardware and register allocation, binding, data path controller generation, and so on. So the security algorithm, which is part of the security framework and also comprises of important information like IP vendor secret information, the encryption key, the security constraints, they all are embedded as part of that synthesis process. So it is actually something known as in-synthesis security. That is, while we do the synthesis, we are trying to encompass security framework into that. Now the automatic question is why? Why do we need to do it in synthesis? What would happen if you do the synthesis and then augment the security framework? The simple answer is, if you do it after you perform the synthesis, it will result into a lot of overhead, because any security algorithm comes with some set of overheads. Okay, that overhead could be space or could be time. Mostly it's about the space. We don't want the security framework to result into design cost overhead. By design cost, I would mean chip area and latency. We would want it to be part of the synthesis so that the entire thing optimizes while the synthesis process is going on. Now, when I say synthesis, I do not mean RTL synthesis. I mean high-level synthesis or architectural synthesis or electronic system level synthesis. They all are referring to the same thing. So once the security information or security evidence is synthesized along with the circuit, then you really get an optimized design that satisfies your area, latency, power, energy, whatever these specifications are provided. And then from the RTL circuit level, you can convert that into its gate level circuit, and correspondingly you can take it into the layout and final fabrication. Now let us have a look at one of the most popular approaches. This approach has been widely used and referred, cited in the scientific community by the hardware security researchers. This is known as triple phase watermark. So what it basically means is that different phases of the design process are exploited to embed different vendor signature information in that. So it uses 7 variable vendor signature encoding mechanism. Okay, as you can see here, it has the 7 variables here, and different variables are actually divided across the different phases of the synthesis process, and it acts as a secret watermark for phase 1, secret watermark for phase 2, and secret watermark for phase 3. Finally, they are unified and a collective signature is formed, which is known as triple phase watermark, which is embedded into the RTL description. Okay, and the description means some goes into the scheduling level, some goes into the hardware allocation level, and some goes into the register or memory allocation level. And that's how you can embed such a secret digital evidence into your design that can act as a detective control mechanism for IP piracy detection later. So this is the synthesized FIR RTL circuit that we designed. And as you can see, by looking at both the diagrams, one is watermark, the other is non-watermark. So you really can't differentiate optically which one is watermark, which is not. So it doesn't give any freedom or advantage to the attacker to remove the security constraints from the design, because if he or she tries to do that, it will actually affect the functionality, and as a whole, the entire structure and the function will be destroyed. So It is an invisible watermark basically. Now let us have a look at the second class of techniques that the researchers have proposed. So this is known as hardware steganography. So the goal here, or the idea here, is that if you have a brand X of integrated circuits in the market, we can detect an IC counterfeit if the brand X has the secret mark of the original vendor. If the brand X has a secret mark of the original vendor, then we will consider that as a not counterfeited design. However, if there is no secret mark, then we may assume that as a counterfeit, because here the secret mark of the vendor is acting as a authentic hologram. In case of cloning, if you want to detect IC or IP cloning, we will have to see and make sure that any other brand, such as brand Y of the IC, does not have brand X secret mark in that embedded. If it does have, then we know it's a copy of the original IP. If it does not, then we can assume it is not a cloned version of the original IC. And the third threat model here is that what if you have an attacker or a fraud owner trying to claim fraudulently the IC IP ownership. So by ownership problem, I basically mean that an IP vendor, an IP seller, once they send the IP to an SoC integrator and an SoC integrator sends it to the foundry, at any stage of the untrustworthy design site or even in the trustworthy design site, an adversary may try to claim the IC IP ownership. In that case, in the IP court, the original IC IP owner has to prove scientifically using forensic evidences that this IC or IP code is mine. Okay. There also, the invisible steganography can play a vital role in proving the actual owner. So let's have a look at the detection process. So in the detection process, as I said, you are trying to look for the stegomark. We call that as a stegomark, invisible stegomark. So in the verification process, if the stegomark is existing, then it's not a counterfeit. However, in case of cloning, if it doesn't exist, then we know it's not a clone version. Otherwise, it is a clone version. So how does it work? What is the basic steganography model? So you have an embedded block, you have the covered design data, okay, that is secretly generated or is generated through some algorithm from the DSP application itself. So the stego key is actually controlling the amount of steganography information that needs to be embedded into the embedded block. And finally, it generates the embedded data. And this stego data needs to be verified at the decoder stage using the same stego key. If the extractor block is able to extract the stego data, then we know that it is actually authentic. Otherwise, the design is a pirated one. So if you look into the system of stego system encoder and stego system decoder, there are two things that are most important. The first is the processing of the designer specific hardware steganography constraints and the embedding of that. So if you think about it at a higher level, there are two major phases. The first is to generate the stego constraints using some steganography algorithm that you have devised as a researcher. And second is you have to find a way to embed those stego constraints into the IP code data path at the RTL level or at the gate level without actually disturbing the functionality and without making it obvious or visible to an attacker. The same information needs to be extracted from either the RTL stage or from the gate level stage, and then you need to perform verification of the original stego constraints with the embedded stego constraints to make sure that this is an authentic design. So this was one of the algorithms that was proposed, which uses something known as key triggered hash chaining based steganography. So this is the entire flow diagram. So you have the DFG representation of the DSP application. You have the module library, which is a very critical information, along with the resource constraint. Now, resource constraints can be designer specified or can be obtained through design space exploration process, which is nothing but a process to find out what is your optimal resource combination based on the given set of specification and constraints. Then you apply scheduling algorithm to develop a scheduled DFG, and from that you can apply different encoding rules to generate the set of encoded bits, which we call as M, because the length of the bit string is equal to the number of operations present in the respective DSP application. These M bits are then further converted into 1024 bits using certain pre-processing rules, such as, for example, the M bit chunk can be appended with 1 followed by a sequence of zeros to generate 896 bits. Further, the 896 bits is appended with the 120-bit representation of the length M to create a chain of 1024 bits. And that acts as the first input of the hash chaining process. You also have an option for stego key block, where you are able to choose which stego key you would like to use through the parallel switch blocks. And finally, it goes through the process of bit padding and hash chaining block to create 512-bit output. So this 1024 bit generates a 512-bit output plus augments 1000 plus augments 380-bit output of the bit padding process plus augments 128-bit representation of the length 512 bits of the previous hash, and finally produces an end 512 bits, which is further subjected to bit stream truncation process, because there the designer has a choice to choose the size of the number of security constraints he wants to embed into the design, and these stego constraint bit stream is then encoded into the set of pairs of the raised allocation storage variables and embedded into the raised allocation phase of the RTL data path, and that actually produces the stego embedded DSP code. So this slide actually talks of some of the existing encoding rules that people have formulated and proposed in the literature, and it can actually act as a starting point of the number of bit stream M, which can further be expanded into 1024 bits. Now let us have a look at the detection process. So in the detection process, the most important thing is to inspect the RTL data path file and inspect the input of the muxes that are associated to all the registers. And we can also inspect the vendor type of FUs, because in case if it is embedded in different phases, such as a raised allocation and FU allocation, then the constraints can be available at different phases. So it's important to therefore investigate both the phases. And then we need to verify that with the stego constraints that has been originally embedded. If they both match, then there is a verification and the ownership is awarded to the true IP vendor. Now, this diagram is actually called colored interval graph, and this is a colored interval graph of finite impulse response filter, and this represents the colored interval graph before steganography is embedded, and this represents the CIG after embedding the colored interval graph. So here the red colored edges are actually indicating the artificial edges that have been added between two storage variable pairs as a result of the stego constraints. This is reflecting the RTL data path of 8-point discrete cosine transformation before steganography, and this indicates the RTL data path of DCT after embedding steganography. The red encircled portions are actually showing the places where the constraints have actually been embedded secretly, so that reflects the changes that have happened. Now let us have a look at another type of methods that researchers have proposed, which is known as digital signature. So it's a novel crypto digital signature based mechanism that incorporates the following security modules, such as crypto hash and RSA, along with multi-level encoding process. So the first step is to generate a bitstream representation of the DSP code. Then we perform SHA-512. Then we perform some post-processing to create an output that is further subjected to RSA encryption. And then we have another post-processing, which is another level of encoding before it finally gets embedded. So you have the crypto hash based on the information of the original circuit or original application. And from that, you can actually produce the hash digest. Use the crypto functions such as RSA to digitally sign the hash using the vendor's secret key and produce the digital signature. If you break up the entire flow into different substeps, we have the following flow diagram. So the inputs is the DFG, which is called the data flow graph of the DSP application. So that can either be a data flow graph or C, C++ representation or any other high-level representation. You subject that to pre-processing, which is to construct the scheduled data flow graph and assign the storage variables. You create the bit stream, which is the phase of initial creation of the equivalent bit stream of the application using some encoding rule. You calculate the digest using secure hashing algorithm. Then you divide the respective digest into m blocks of size n bits and convert each of these n bit block into a decimal value and feed it into an RS encryption system. This RS encryption will work with some private key of the IP vendor and it will produce a final bit stream from the encrypted decimal value. Then using another encoding rule, you can actually encode each of these bit streams and finally produce the respective security constraints that can be embedded into the design during the registry allocation phase. So RSA, as we know, is an asymmetric key encryption algorithm in which two distinct keys are involved. And as I said, it is used to digitally sign the hash of the vendor's secret mark information to ensure authentication of the genuine vendor. So as an example, if you have 120-bit, secret private key and the information equivalent of that in terms of the RSA input and output is shown here. So this is the RSA decimal input, this is decimal output, and this is the binary equivalent. So once we have that done based on the M chunks, we will concatenate all these encrypted binary values to produce a large size digital signature. Now in the embedding phase, as I said, the IP vendor can actually use different encoding rules. So you may have, for example, bit 0 encoded in a way that an additional secret edge is added between the node pair prime in the colored interval graph. Or you can have bit 1, which is an additional or artificial edge added between the node pair even in the colored interval graph. So this is an example. Of course, you can have different encoding mechanisms in place. But this is actually trying to ensure that you're inflicting and implanting as many secret information into your colored interval graph that remains undetected and that remains unperturbed in terms of the end functionality, because you don't want to touch the end functionality of the CIG or the registry allocation phase or the other phases, because once there is any change or disturbance in the functionality, the entire synthesis process gets disturbed. So this is another example of how the encoding works. So you can have operation number and the control step number both even, and you can encode that as bit 0. You can have odd even, encode that as 1. You can have even odd, that also encoded as 1. And you can have odd encoded as 0. So we can devise different encoding mechanisms for the operations. So using that encoding mechanisms, if you have a scheduled data flow graph of a discrete cosine transformation example shown on the right side, you can actually have the following bits generated from here. So since there are 15 operations, so 15 bits have been generated corresponding to this DCT application. Now, hardware security, you need to understand that whatever algorithms you're devising for security, you must have design cost overhead as minimum as possible. Of course, 0% is the best number. And whenever you want to compare with any existing state of the art, you need to make sure that your design cost is lower than that. And as you see here, that for following hardware accelerators like bandpass filter, JPEG sample, MESA, JPEG, IDCT, ARF, and so on, we mostly have seen that we have not been, having any overhead in the different digital signature sizes that we have chosen. Okay? Because the design cost pre-embedding and design cost post-embedding is pretty much similar. Of course, there is some changes in the design cost as you keep increasing the digital signature size, because that is adding more constraints to that. The next thing is to evaluate in terms of security. So we have something known as probability of coincidence, which is a measure of the amount of digital evidence that is embedded into the design, and how much what is the probability of detecting security constraints in an unsecured design. So lower is the PC, the more robust the design is therefore considered to be. So as you can see across the different DSP applications, the value of PC is actually reducing as you keep increasing the digital signature size. Now let us have a look at another type of hardware security technique, and it is using something known as biometric fingerprinting. So it's part of digital forensics. So here the IP vendor's fingerprint can actually be used and converted into its respective digital template, and that can be embedded into the IPIC so that it can guard against piracy and fraudulent claim of IP ownership. So when you capture the IP vendor fingerprint using an optical scanner, of course you need to make sure that it undergoes using pre-processing algorithms such as FFT enhancement, binarization and thinning, and you capture the minutia points and convert those minutia points into its respective digital template using some algorithm. And then these digital template corresponding to the biometric fingerprint is mapped into respective hardware security constraints and implanted into different phases of HLS and RTL synthesis. And finally, you have the biometric fingerprint implanted hardware accelerator design. So you have an input fingerprint, and you converted that into a binary image followed by thinned image, and then you have the minutia points. As you can see, the minutia points, different types of minutia points have been captured here, and they will be used for converting into its respective digital template value. Now let us have a look at the different fingerprint images and how much impact it has on the minutia points. So as you see, different fingerprint images generates different minutia points, and you can therefore control the size of the digital template as per your choice. So depending on the size and complexity of the application or circuit, you can actually decide what amount of secret digital information or security constraints will be implanted into the design. So as you can see, the first one has 526 bits, second one has 350 bits, and the last one has 555 bits. So it can vary across different fingers of an IP vendor. Similarly, this shows the variation across little finger, middle finger, and ring finger. Again, you have different variations of the digital template sizes. Now, these fingerprint, biometric information has been implanted into JPEG codec hardware accelerator while we designed it. And as you can see that the one on the top, this portion is the one where most of the fingerprint information has been embedded. So that's why we have circled that in red, although it's an invisible fingerprint. Now, how to detect the biometric fingerprint, okay, when it comes to the point of authentication and verification? So the first thing is we need to match the number of constraints in terms of number of zeros and ones in the digital template. If it matches, then we move to the positioning matching algorithm, where it matches the exact positions of the zeros and ones with the digital template and the one that has been embedded. If there is a true match, then we know that it is an actual owner. If there is any mismatch, then we know that it's a false claim of IP ownership and the design is tampered one. Now, looking at the variation of minutia points, you see that different fingerprint images have a lot of variations, and that actually impacts the probability of coincidence drastically. So the lower, the better, because the more stronger and robust digital evidence you have, the more stronger security constraints you will have in order to justify your ownership, as well as to make sure that it's an authentic design. Again, you have to make sure that the design cost doesn't change. So as I told you before, that before and after implanting the biometric fingerprint or any watermarking or steganography, you need to make sure that the design cost doesn't increase. So it has to be perfectly 0% overhead. Now, based on all the algorithms that I have been speaking, okay, for last some time, some public hardware security tools have been released by our group in September 2020, and these 4 are currently available in in the different centers, and I will show you where these are available. So the first one is Phasiometric Hardware Security Tool, which is part of the CAT4 assurance, and it's available in the link here and hosted at University of Florida Cybersecurity Center. So you can actually visit this site and you can download this tool for free for using and for experiment and research purpose. And the development of these tools are part of CAT4 assurances sponsored by IEEE CIDA, IEEE Hardware Security and Trust Technical Committee, and Warren Nem's Institute for Connected World at University of Florida. This is the second one. This is based on cryptosteganography, and this is available here. And this is also, deploying a combination of steganography and cryptography together to handle the threats of IP piracy, IP counterfeiting, fraudulent claim of IP ownership, overproduction, and so on. And you can also have a look and learn about the different types of threats, such as, for example, IP piracy. If you go to the website of CAT4 Assurance, you will see that it actually talks about a lot of useful information, and it says that in case of IP piracy, an IP designer in the third-party design house may illegally pirate the IP without the knowledge and consent of the designer. So here, the IP piracy is actually a threat, to the actual IP seller. So either the SoC integrator or somebody outside the SoC integrator house can actually pirate the original IP made by the IP seller or IP vendor without his knowledge. So he needs to make sure that he has proper, digital evidence in place in order to secure and safeguard his design. So a lot of tools have been devised and made publicly available. So of course, a few of these tools are from my group and few are from the other groups. And its corresponding publications and the algorithms have also been provided here. So, for example, the key chaining or key triggered hash shading based crypto tool that we have designed, that is available here. And there's one more else that is talking about obfuscation through security aware on chip memory. That is from Ankur Srivastava group in US. So his tool and his details are available here. We have made something known as structural obfuscation and cryptosteganography for medical imaging systems, that is available here, as well as something on endpoint DFT. So you can actually visit this site and have a look at all the hardware security tools and their algorithms that people have been working. So I would like to take a pause here and would like to keep it open for some questions before we move into the next phase of the talk. Do we have any questions or any doubts or anything from the audience who would like to ask questions on hardware security so far? Am I audible to all of you?
My on for all, and they can ask directly.
Please make sure or feel free to make it interactive because it's an FDP after all. Even people who want to start working on this area for the first time, I would encourage you to ask me questions.
Hello.
Yeah, I can hear you.
Sir, true random number generation using data encryption. Data encryption using a cryptography and FPGA techniques will be uses in that scenario. Basically, pseudo random number generation to random number generation for data security and authenticated for using the tree-based interleaver or shift register. So related work will be used because this is my core area of quantum C4 registers as well as for.
If I understand your question correctly, because there was some disturbance in the mic. Yeah, sorry, I may not be able to understand your question correctly.
For a random number generation using a post processor, XOR gates, for data encryption methods in cryptography security.
Fine. So if I get your question correctly, you're talking of TRNG, True Random Number Generator.
Yes,
So,
yes.
so PRNG, TRNG, these all have been actually, been looked into and have been researched and have been published long time back for different security purposes, for data security and hardware security both. So if you're planning to work on it for your research, you will have to be a little careful so that you don't reinvent the wheels and don't keep working on things that have already been done. However, TRNG is mostly used for puff, and also used for generating fingerprinting information. So you will have to be careful on what purpose you're actually using TRNG for. If the purpose of using TRNG is for generating, secret key or for logic encryption purpose, then it has already been published and already been done way back in the literature. But if you're trying to use it for and merge it with cryptography for IPP, which is IP core protection against piracy and these attacks, then I think you may think of doing it. However, with the intention in mind that you have proper detection and verification mechanisms, because random numbers are hard, when you want to detect it later. And if you do not have proper mechanisms.
Hello.
Yeah, please go ahead.
Sir, basically, sir, jitter and FPGA techniques and using a tree-based random interleaving, both odd interleaving and even parity generation, random interleaving tree-based type structures in cryptography. This is a core area of my research interest in basically efficient approach of true random number generation, pseudo random number generation using a data encryption method in security as well as for cryptography algorithm. So for generating how many of randomness use calculation, basically different parameters like entropy, throughputs, power consumptions, as well as efficiency using a different type of multipliers, Vedic multiplier.
Hold on. I think you're mixing up a lot of things together. Let's go step by step. What is a threat model that you want to address?
Yes. This is a main as a true random number generation using FPGA and using data.
I'm saying what is a threat model that you want to address through your method? What threat are you trying to handle through your method?
Basically, sir, true random number generation using a tree-based interleaver and data encryption.
That is a method. I'm not talking of the method. I'm talking of what is a threat model that you want to address through your method. Which threat model?
Main model is sir XOR and CPO register will be used for calculation of final CPO and FIFO method.
No, I think you're not getting my question. So you're focusing on the method and I'm focusing on the problem. I'm asking you what is the security problem or threat model that you want to address? Please answer that first.
Yes. Security aspects as well as for randomness calculation.
Security
as a proposed method.
What security are you trying to do? Are you talking about hardware security or data security?
Yeah, I have first of all for both security and data security as well as for encryption, decryption, hardware security. Hardware security in terms of FPGA prototypes regarding.
So when you're talking of FPGA, which block or which architecture of FPGA are you trying to target? Are you talking of configurable logic blocks? Are you talking of VRAMs?
Seed random number generation, like schematics of 3-ring oscillation, 5-ring oscillation, shift register, pre-processor and post-processor using a 4-class multiplexer model will be used. Post-processor.
I think you need to have clarity on the architecture first of all. I think you're mixing up a lot of things, which makes it difficult for me to answer what exactly you're seeking for. You need to have clarity on the architecture and you need to have clarity on the threat model. Are you currently doing PhD or what is your status?
Yeah, I have a MTech final year.
Okay, you're doing MTech finally. Okay. So my suggestion would be to have some clarity on what threat model you're handling, because you're mixing up data security, hardware security, FPGA, power, ring oscillation. You're mixing up a lot of things.
Yes, sir. Both proposed use for true random number generation and symmetric cryptography, as well as, sir, first of all, sir, proposed method is tree based interleaver, random interleaver, or interleaver, and even interleaving process, and calculation of randomness using different types of the CLB blocks, like using a preprocessor, 4-bit C4 registers, 3-stage ring oscillator, and 4-stage ring
You don't
oscillator.
need to repeat this information. I've got this. What you're saying. You don't need to repeat this. You're
Different
not.
type of
You're
different
not
shift registers, type of
asking the
content shift registers,
asking for.
counter, down counter, as well as say up shift registers, down shift registers. You will be uses in the proposed method.
I think. Did you get what I said to you, or did you not get what I said to you? Did you understand what suggestion I gave you in order to move further
Yes,
in
yes,
this area? You need
yes,
to
yes. Okay.
differentiate between data security and hardware security. Don't mix up two things together. And first of all, have focus on what threat model you want to address and what architecture and FPGA you are targeting for safeguarding against different hardware attacks. So focus on that first.
For hardware security, first of all, sir.
If you're talking about FPGA hardware security, then you need to focus on something known as side channel attacks. Okay, side channel attacks are the ones that are actually mostly deployed on FPGA. You need to find out ways to handle side channel attacks. When I'm talking of side channel attacks, what I mean is you need to find out ways to do differential power analysis, correlation power analysis, so that you are able to detect any sort of attacks that uses side channel parameters and launched into an FPGA. Okay, again in FPGA it is classified. It could be CLB based FPGA, it could be DSP48, it could be VRAMs, and so on and so forth. There are different papers that have targeted on different architectures for for safeguarding against different hardware attacks. So you need to focus on those things explicitly, and then you need to think of how you can safeguard them against different side channel attack parameters. If this is the goal, that you want to secure FPGA against hardware attacks, so this is the way to go about it. But if you're thinking of data security, then that is a completely different branch than what we are actually talking about today. Data security, if you're talking about leakage of secret key information, because that is also very important data that is actually part of the previous security, then in that case you need to have advanced encryption system or advanced encryption standard algorithms merged with different Prof based techniques, so that you can actually secure your data against different side channel attacks as well. So think on those lines so that you can actually move forward and have some mechanism in place that can actually handle hardware security of FPGA as well as data security in terms of leakage of secret key information from an FPGA device. Is that okay?
Okay, sir. Okay. Yes, sir. A different type of multipliers, sir. Vedic multiplier or different type of multiplier regarding that.
You can use different multipliers. There are a lot of multipliers, Vedic multipliers, and different types of multipliers that you can deploy, but that has no effect in security. That can only help you in getting an area delay trade-off in having better optimization. Nothing else, nothing more than that.
Yes, different types of a number of LUTs, number of CLB blocks, configurations.
All of those. That's what I said. Lookup tables,
power delay, sir. Power delay and power throughput consumption. How the efficiency will be, and as an overall randomness of post processor will be generate calculation of different type of part delay. Part delay in terms of randomness in terms of different number of LUTs will be used in the system configuration model.
Do you know what is inside an LUT first of all? Do you know what is inside an LUT?
Different types of characters, von Neumann characters, XOR based preprocessors, and BCH code characters will be using for calculation of.
What are the exact things inside the lookup table? Don't confuse between von Neumann architecture, Harvard architecture. Don't use those terms here. They have nothing to do with this here. Tell me precisely what are inside an LUT. You need to look into it carefully. I think you're throwing up a lot of words which have no sense and no relevance to what you're talking about. You're randomly using a lot of words here and there. Don't do that. Otherwise, you won't have any focus on the research problem. If you're talking of LUTs, or if you're talking of CLBs, which is configurable logic blocks, you need to look into exact relevant papers that have done security of CLBs in an FPGA against side channel attacks. Because there are different papers that have done protection against CLBs from side channel attacks, protection of LUTs from side channel attacks, protection of DRAMs from side channel attacks. So every paper has a specific target architecture in mind. Okay, so you need to see which exactly is your suitability. That is why I asked you right at the beginning what type of FPGA architecture you want to handle. Okay, you cannot have one unified algorithm for the entire FPGA architecture because FPGA architecture is also quite complex. You need to break it up into different parts and you need to have different security algorithms for different blocks of an FPGA architecture. Okay, and please focus on side channel parameters, side channel attacks, because that is the one which is currently the state of the art on FPGA. If you are able to guard against side channel attacks and beat any of the state of the art in terms of security and overhead, then your method will be a better one and publishable one.
Okay, sir. Thank you.
Welcome. Any other question from anyone in the audience? Okay. So what is the way ahead? Shall I continue or should we have a break of 5-7 minutes before we move on to the next phase?
Sir, we can have 5-7 minutes break, sir. Then we can continue.
Okay, fine. So we will join back in 5 to 7 minutes.
Okay, okay. Thank you.
Rahul?
Yeah, yes, sir. Yes, sir.
Yeah, I think we can resume.
Yeah, yes, sir.
Okay, so welcome back. We are now moving into another dimension of hardware security that uses biometrics, and we had already covered one of the angles using fingerprinting. Now we're moving into the next branch, which is on palm print. So palm print has its own set of advantage compared to fingerprinting. So first of all, it's a contactless mechanism. Second is palm print is not subjected to any injury or external parameters. Thirdly, it doesn't need an optical scanner, so that is a big advantage, because optical scanner you're investing money, as well as you need to ensure that your fingerprint is properly placed on the surface area of the optical scanner in order to capture maximum number of minutia points. So those advantages palm print biometric offers compared to fingerprint. Now let's have a look at the algorithm. So the first thing is you have the IP vendors palm print, along with the resource constraints, module library, and the algorithmic representation of the DSP application. All of these are fed as a primary input into the hardware security methodology, and the vendor's palm print is captured along with its grid size and spacing information, and that is used further to derive the nodal points on the palm image. When you derive the nodal points on the palm image, you need some information such as palm print feature set. So you need to have the predefined feature set available with you. And this nodal points will then be subjected to another process, which is used for naming the convention on the nodal points, followed by generating the image with the palm features. Finally, the palm features will be used in order to determine the feature dimensions between the nodal points for the selected palm features, and finally the different feature orders are decided in order to generate the palm print signature. This palm print signature is then subjected to hardware security constraints using some encoding rules, and you then implant the secret information in the HLS framework. And finally, you have the RTL data path, or the gate level design of the DSP application or DSP coprocessor with the palm print signature implanted. So when we have the capturing stage, at first the palm print biometric of the authentic vendors is captured, and it is subjected to specific grid size and spacing, and this helps in generating the nodal points precisely. Then you can actually choose the palm features and then calculate the feature dimensions of the different palm features and give a specific naming convention. So as you can see in the diagram, we have a lot of palm features which we have demarcated, such as DFM, DFF, DSF, DSM, and so on, and they actually represent the different geometric dimensions of your palm print. Now let's have a look at what these are. So basically there are different features. There are specifically 19 features that have been selectively shortlisted from the palm image. And the first one is the distance between the start of lifeline and the end of lifeline, which we have designated as DL. And the naming convention is between P16 to P24. The next one which we have in place is the distance between the datum points of headline and the lifeline, which is DHL, and it's between P23 and P24. So if you look back into the diagram, we will have a look at it. And that is reflecting the coordinates between 405, 520 to 25, 650. Then we have the width of the palm, which is between P16 and P20, the length of the palm. Then we have distance between first consecutive intersection points of forefinger, which we have named as DFF. You have the distance between second consecutive intersection of forefinger, which is DSF. Then between the third consecutive intersection, which is DTF. And FX stands for the first consecutive intersection points of the middle finger, which is DFM. Similarly for the middle finger and the ring finger. Then you have something known as distance between first consecutive intersection points of middle finger and the third consecutive intersection of middle finger, and so on. You also would like to capture information from your thumb. So we have moved into the evaluation of the distance between second consecutive intersection points of thumb finger and the distance between starburst point and the third intersection point of the thumb, which we've indicated as P19 to P22. So these are the selected 19 palm features and its corresponding nodal points and its corresponding coordinates. So Manhattan distance formula is used in order to calculate the exact feature dimensions, which are then converted into its respective binary, and then the concatenation of the different palm features are performed as per the feature order decided by the IP vendor, because that is a secret information only known to the IP vendor. Therefore, it adds to the security value of the algorithm. Now, for example, if the feature order is DL concatenated with DHL, concatenated with DTT, and so on, where you have the concatenation operator represented through the symbol, and you have the corresponding feature dimensions and its binary representations as follows. You can have an entire palm print signature obtained by a combination of these different parts of the binary or digital template. We note here that the size of the palm print signature varies based on the number of chosen palm features by the vendor for signature generation, and therefore it adds to the security value and security strength, because depending on the required security strength, the IP vendor may reduce, edit, or add certain palm features into the feature set. Now we derive the covert security constraints and implant it into the target IP code design. So this is how the register allocation information of the target hardware IP code looks like. So we have the encoding rules in place for the signature, and post obtaining the digital template, we generate the respective hardware security constraints. The shaded portion here is actually reflecting the different portions of the register allocation phase where the secret information has been included. For example, in the sample design having 31 storage variables that have been executed through 8 registers as an example, the security constraints for zeros can be between T0 to T2, T0 to T4, T16 to T20, and so on. And as I had said earlier, that we evaluate the security in terms of two major metrics. The first is probability of coincidence, and second is tamper tolerance ability. So in tamper tolerance, we have P to the power Q, where P is actually talking about the number of encoded variables used in the signature, and Q stands for the signature strength. Okay, whether it's for fingerprint or palm print or watermark or steganography and so on. And comparative analysis of probability of coincidence with the tamper tolerance with respect to the state of the art has actually shown a lot of advantage in terms of reduced PC value for different benchmarks and higher tamper tolerance ability, because that actually reflects the signature space, okay, that is acting as a guard against brute force attack. So therefore tamper tolerance is a very vital parameter to prove how good is your algorithm against brute force attack, and probability of coincidence is actually reflecting how good it is against different sort of tampering attacks. In terms of the design cost metric, as you see, we have a weighted metric, normalized weighted metric in terms of the design latency and design area. So here latency is actually in terms of nanoseconds or in clock cycles, and area is basically in terms of the number of gates or in terms of the cell area value in terms of micrometer square. So we have normalized it so that we can have a design cost value between 0 and 1. Okay, and H1 and H2 are the two weighted metrics that is actually indicating the priority given to the latency metric and to the area metric. So what are the key features? So you have a contactless palm print biometric that is used for securing reusable hardware IP code. It also enables seamless detection of pirated counterfeited DSP IPs used in consumer electronic systems and in IoT frameworks. You also have, therefore, safety against consumers, as well as you're protecting the IP brand value, as well as resolving the traffic bleed. And any DSP IP code can be embedded with such palm print signature in order to distinguish between authentic and its pirated or fake versions. Furthermore, the palm print constraints are non-replicable and non-vulnerable compared to other hardware security techniques such as steganography and watermarking. And finally, it is much more robust and provides stronger security and minimal design cost overhead in parallel compared to existing state-of-the-art. Now let's move into another application or another dimension of hardware security. Here we are basically talking about something known as image processing filters that are often part of several medical imaging systems as well as multimedia applications, as well as used in machine learning algorithms. So this slide actually is talking about how to design an obfuscated 3x3 image processing filter hardware that has reconfigurable functionality. So you see on the right side, we have a scheduled DFG of the generic 3x3 image processing filter. So this image processing filter is actually working on a 3x3 image, and it can perform variety of functions such as image blurring, image sharpening, image embossment, and image edge detection using Laplace edge detection algorithm. And if you convert it into its generic mathematical form in terms of the pixel value, this is how the equation is represented as, where I00, I01, I02, these are actually the pixel values of the images, and H00, H01, and so on is actually the filter coefficient value based on the kernel matrix of the image processing filter. So when you convert that into an equation form and you therefore generate the data flow graph and its scheduled version, this is how the entire graph looks like in terms of pixel value 00 and pixel value 01. And you see that what we have done here basically is we have used convolution operator, because the image matrix is sliding across, the kernel matrix is sliding across the image value. So when you convert that scheduled data flow graph into its obfuscated form, we basically use different high-level transformation techniques such as compiler-driven transformations such as loop unrolling, loop folding, redundant operation elimination, loop invariant code motion, and so on, that actually is applied at the graph level, which therefore has a direct reflection at the RTL level once you deploy high-level synthesis. So this is how it basically looks like. This is how the data path of the image processing filter looks like. And we have also added a reconfigurable functionality on the top by adding different 8:1 multiplexers, so that it is able to control the different filter type functionality based on the selected key values of F0, F1, and F2. So if it is 000, it performs as a blur filter and it takes the kernel coefficient value of HPQB. If it is 001, it is performing sharpening filter. If it is 010, it is performing as vertical embossment, and so on. Similarly, we can do it for individual image processing filters such as blur filter. So the one on the top is actually structurally obfuscated blur filter hardware accelerator, where you feed the input image, it goes through some pre-processing step, and it produces the output in terms of the convolved filter matrix, which after post-processing you can get the blurred filter image. Similarly for sharpening filter, similarly for the vertical embossment, horizontal embossment, and Laplace edge detection. And these IPs are used in several applications in camera and smartwatch and in other consumer electronic devices. Now let's have a look at the role of hardware security in medical imaging systems. Okay, how we can make sure that the medical imaging systems do not provide us with corrupted data, specifically in case of CT scans and MRIs. So as we know, in the modern age healthcare systems, we heavily rely upon electronics and internet technology to accurately and rapidly diagnose and provide advanced treatments. Here, the electronic hardware are critical in healthcare systems for processing of medical data, whether we are doing, image compression, image decompression, filtering, and so forth. Furthermore, you have the internet technology that acts as a pivotal mechanism in transmitting the medical data for teleradiology and telepathology. So what is critical here is therefore the size of the medical data, which we all know that is generated from computer tomography or MRI, is actually huge, and therefore it requires large storage mechanisms to store and process them locally. And more so when you transmit them over the internet, in case of remote diagnosis, it needs huge bandwidth. So we therefore cannot store such a large size data. So what is typically deployed is something known as hybrid compression mechanism. So in hybrid compression mechanism, what happens is in the region of interest, in the medical imaging data, the compression is not performed, and in the remaining part of the images, it is actually compression is performed using lossy compression techniques. So just to give a small example, CT abdomen image comprises of 400 images, and each slice contains around 512 cross 502 pixels. And assuming that 16-bit size of each pixel, the whole data of the CT abdomen is therefore 150 MB, which is huge. And therefore we need compression techniques. However, the problem is if you try to compress, you may actually lose the essential information of the medical data. So that's why we have this hybrid compression in place. So what to do and how to ensure that the hardwares used in the imaging medical systems, they do not generate corrupted data. Now, if the JPEG codec processor that is part of the imaging modality in imaging medical systems, if that is somehow corrupt, okay, either due to backdoor Trojan infection or due to pirated version, then it may have a tendency to generate corrupted data or data that is not accurate. Okay, so the goal is to keep intact the correctness of the generated compressed pixel data so that the region of interest in the medical imaging data does not get compressed, okay, inadvertently. And when doing that, we need to therefore ensure that the JPEG compression hardware is authentic and secure. Okay, so how to do that? So that is the most important thing. So we need to have mechanisms that acts as preventive control, and we also need to have mechanisms that acts as detective control. Okay, let's see how to do that. But most importantly, these medical imaging data are extremely crucial for the treatment. So if there is anything wrong in terms of the compressed data of the medical imaging systems, then it can actually lead to false diagnosis of diseases and wrong treatment of patients, which we definitely need to avoid. So you have the acquiring of the images from patients' internal organs, and you subject that to internal JPEG compression chip. Okay. Now, if the JPEG compression chip is an unsecured version, as you see on the top, there is a possibility that it may produce possibly corrupted computed information in the compressed pixel values of the medical images. Because if it is unsecured, it is actually open to Trojan insertion, counterfeiting, and cloning. These are the threats. And we need to have first line of defense using obfuscation to somehow thwart Trojan insertion and reverse engineering. And we need to have second line of defense using steganography to have detective control against counterfeiting and cloning so that it can be isolated before integration, which usually the secured JPEG codec processors are capable of doing. So we have these three threats, and we have a preventive control, that is thwarting mechanism, and we have a detective control, this is detection, and we are able to make sure that we have structural obfuscation in place so that it actually makes it difficult for an adversary or an attacker to analyze the hardware and insert Trojan in safe locations. The reason for identifying safe locations in the netlist or in the RTL circuit is because so that it remains undetected during normal testing and simulation or even during manufacturing testing. So that is the basic goal here. Now, when we have designed our secured JPEG codec IP for medical imaging systems in terms of structural obfuscation and in terms of hardware steganography, we have realized that it is able to produce the pixel accurate values even though we have compressed it at Q90 and again reconstructed the CT scan images using JPEG decompression hardware. So we have exactly got the same images pixel by pixel. So there weren't any corruption of data. Now let's move into another side of hardware security that deals with something known as functional obfuscation or logic encryption. So as you see, I have put here a flow, and you have something known as a DSP application. You have the original netlist of the IP core, which is subjected to HLS, RTL synthesis, gate level synthesis. You perform functional obfuscation in order to generate the locked netlist of the IP core, and that is then part of the C device IC RTL netlist, which is subjected to the layout to get the JDS file, which is sent to the fabrication foundry, and you have the masked version of that. Now, reverse engineering can actually be deployed in using any of these information. So you can have reverse engineering that is, using information from this netlist, from this JDS file, from the mask layer, and from the non-functional IC, and also from the functional IC, which is market ready. The goal is to have the lock netlist, which is this one here. The goal is to have this from any of these stages, so that the attacker can actually use it if using different attacking mechanisms to decipher the netlist. Okay. So, what is reverse engineering? We have to first understand. It's a process of gaining complete understanding of the functionality, design, and structure of the DSP design. And RE can be used for dishonest intentions such as overbuilding, piracy, and counterfeiting, or even for insertion of malicious logic such as hardware Trojan. Now, once you have the functional obfuscation or logic encryption in place, it is actually able to guard against reverse engineering to some extent. It cannot totally prevent it, but it can thwart it. It can hinder the attack. Now, when I say logic obfuscation, we need to understand what are the possible threat scenarios first. So, at the gate level, these are the three main threat scenarios. The first is, we call it as sensorization attack. So, sensorization attack can be launched if you have an isolated key gate. So, isolated key gate means if there is no path between K1 and K2, and they are therefore known as isolated gate. As you can see here, there is no common path between K1 and K2. So, attacker can sensorize the value of K1 as 0 to the output O1 by applying a particular input pattern here. Secondly, if you have a run of key gate, that is, if a set of key gates are connected back to back, it increases the likelihood of generating the correct key combination. So here the goal is that you should not have run of key gates, because then in that case you will have multiple key values that produces the key value to the output. And finally, something known as concurrently mutable key gates, that is, if two or more key gates converge but have no common path between them. So in this case they are trying to converge but they have no common path. So here if you apply I6 equals to 0 in this, so it will actually mute the key value K2, and therefore K1 can be sensorized to the output. So these are the things that should not happen, okay? Because if it happens, then launching sensorization attack becomes much easier. Now, as I said, if you want to launch sensorization attack, the attacker can extract the keys of the locked netlist. And to mount this attack, the attacker also requires a functional IC along with the obfuscated netlist that he can get using reverse engineering attack. So the goal is to prevent it, basically. The other type of attack is called as SAT attack. Here the attacker needs the locked netlist and the activated functional IC. So the SAT attack algorithm firstly generates distinguished input-output pairs using SAT formula, and these distinguished IO pairs can be exploited to eliminate the wrong key combinations, as long as we have elimination of all the wrong keys possible. So SAT works like that. So the design should be such that SAT attack should not be possible. And finally, you have something known as removal attack. Here the goal is to remove the logic encryption key gates from the design totally, so that when the design gets synthesized, the keys do not play any role in the encryption. So it tries to eliminate the additionally inserted key gates. So they have sophisticated detection algorithms and tools in place in order to do that. So, one of the ways that have been proposed in the literature is to have something known as IP code locking blocks. So these IP code locking blocks contain 8-bit key values inserted into each bit of the output data. That is, in order to decode each bit of the output, you need to know the exact key values of K1 to K8. Okay? And they're usually designed using different combinations of AND, NAND, NOT, XOR, and NOR gates. And the structure of ILBs also depend on what is the key value that is fed. So these are not fixed architectures; they are reconfigurable architectures. Okay, that will be reconfigurable, subjected to the incoming values of K1 to K8. So we'll see how that is done. So suppose you have these reconfigurable ILB structures inserted into the gate level structure post HLS, post RTL synthesis in an FIR design. This is a small example of a 4-bit FIR. The red colored gate structures are the ILBs that have been inserted that acts as logic encryption things for performing functional obfuscation, and they have actually been generated using something known as reconfigurable logic, which I'll take you directly to here. So these custom hardware that you have that can be built using secure hashing algorithm or that can be built using advanced encryption standard hardware IP, they can actually generate different bits, and those bits, if you divide it into different 8-bit chunks, because you have 8-bit key values, so there will be possibility to cover 64 ILBs in the encrypted design. So all those 64 ILBs can actually be reconfigured using these 8-bit values generated through SHA or using AES. So that's why we don't know what is going to be the output value of SHA and AES, because that is controlled. In case of AES, it is controlled using 128-bit private key, and in case of SHA, it is actually controlled using the input 1024 bit. The remaining ILB blocks are non-encrypted ones, so they can be in the design as it is. Now let's see what are the features of this approach. So first of all, in order to decode the SHA value, the attacker needs to find out the 1024 bits of the plain text input. Further, the attacker also needs to know the architecture of the 64-bit reconfigured ILBs. Now, as I said, it is not a fixed architecture. So since there is no fixed architecture used, so detection of such ILBs at the gate level becomes hard post synthesis. And third is, in order to reconfigure up to 64 ILBs, only one SHA block is used. Therefore, it doesn't add any area overhead into the design basically. And in case of ILBs, the structures are reconfigurable, and because of its reconfigurability, feature, it is therefore possible that all these basic gates can be used in order to have different ILB structures. Okay, so therefore, detection of ILBs in the complex DSP design becomes extremely difficult, as it is not known to the attacker what type of ILB architectures are used. Further, post synthesis, the ILB gate structure becomes camouflaged because everything gets converted into an optimized basic gate form. So it becomes further difficult for an attacker to identify the exact gate structures that are used as part of this. And finally, the crypto hash function provides strong security features such as collision resistance, pre-image attack resistance, uniformity, and deterministic features. So that's how we handle the removal attack. And one of the most vital things in case of DSP applications is DSP designs are inherently resistant against SAT attacks, because SAT attacks mostly use CNF, conjunctive normal form representation first in order to launch the, the input-output distinguishing pair based approach. So converting a DSP application entirely into a CNF form is almost literally impossible, because CNF form basically in case of multipliers will be very complicated, because it advances through a set of shift add and so on. So the conjunctive normal form becomes huge. So therefore, in order to launch SAT attack, the conjunctive normal form designation is not possible in case of DSP. So SAT in DSP applications are inherently resistant against SAT attacks. So SAT attacks are therefore out. We have taken care of removal attack. Key sensitization attacks we have taken care of by having 8-bit key inputs in order to decode 1-bit output in the design, as I have spoken earlier in case of this. So all the 3 attacks that are possible in order to decrypt the logic encryption in the netlist is therefore taken care of. And if you move a little bit deep into the SHA architecture that are used for guarding against removal attack, this is how it basically looks like. We have a custom SHA logic, which is an 8-bit input, and it produces a 512-bit hash digest, which is again further divided into K1 to K64, so 64 blocks. And each of these are therefore used for ILB key extraction logic. That is, in order to generate n ILBs, each of 8 bits, we would use this custom hardware for SHA-512 in order to add it and augment with the ILBs that you have. Okay, so we have covered a lot of hardware security aspects today, but the goal is whenever you work on hardware security, we need to take care of the energy security trade-off angle, and that is the future, because for any framework, whether it's CPS, IoT, or consumer electronics, the goal is to have the trade-off between energy and security ultimately. Thank you, and we are open for questions.
Yeah, thank you, sir. Is there any question?
Yeah, good evening, sir. I have a question.
Yeah, good evening. Please go ahead.
Yeah, so sir, we have seen, so you have told a lot of designs, a lot of filters, a lot of hardware things. Sir, is there any generic model or is there any specific attacker model we have considered when we design this security for this hardware? So, what kind of model we are targeting?
So I'll take
Adversary.
you
What are
back.
the capabilities of adversary?
I'll take you back to the original part of the first half of the slide, and I have put up a model here. So this is the basic security model that you need to always remember. Okay, when we are talking of hardware, this is the flow, and this is the entire cycle. Okay, and every stage of the SOC cycle has its own set of attacks and vulnerabilities. So if you're trying to target IP piracy, so that is the threat model that is available at the SOC integration house. Okay, so Trojan attacks are also possible. So for example, I'll make it simpler and make you understand. So if you are an IP vendor and I'm the SOC integrator, so what typically happens is everything in the global supply chain is outsourced. So I won't want to make my SOC totally, internally in my design house, and I will actually outsource the design of my IPs to the third-party IP vendors. So you could be one of my third-party IP vendors, somebody else could be the other third-party IP vendor for the second IP, and so on. Now all those third-party IP vendors are basically untrustworthy. And I, as an SOC integrator, I would not have complete trust. So therefore, I need to make sure that all the IPs that I'm actually importing before integration, it goes through the checks of piracy, counterfeiting, and cloning. That is, I inadvertently don't want any IPs that are not original to be embedded and integrated inside my SOC. So that is my model. As an SOC integrator, that is my security model. Now, as you are the IP vendor. For you, what is important is if you are the actual or original IP vendor, you would not want your IP to be, pirated or cloned without your knowledge, because you have ownership rights on your IP. So therefore, you need to have ownership secret mark in your IP design before you send it to an SOC integrator. Because SOC integrator could be untrustworthy to an IP vendor. And even if an SOC integrator is trustworthy, an SOC integrator has to anyway send the design to the foundry for converting it into its fabricated form. Now, foundry is again untrustworthy. So therefore, an IP vendor always wants to add his secret security information so that it doesn't get pirated without his knowledge. So that is the other angle of the security. So that is when we have this angle of fraudulent claim of IP ownership and IP piracy into the picture. Now the the angle of Trojan now comes into the picture when I, as an SOC integrator, since I do not trust the incoming IPs, I also do not trust that whether these IPs have any backdoor Trojan logic like hardware Trojans inside it. It is possible that they may have. So I should have proper detection and isolation mechanisms as an SOC integrator in place so that I may be able to detect if there is any functional Trojan in my incoming IP. If there is, I need to identify and I need to isolate. So that is the another security model from the SOC integrators perspective. Okay, that's when the Trojan attacks come to the picture. Now going into the stage of overproduction. Now when it goes to the foundry level also, it is possible that somebody can overproduce by stealing the IP. So that is another security model there. where the SoC integrator and the IP vendor both needs to have proper security mechanisms in place so that they may be able to detect any overproduced IC at the foundry level. Okay, if they're able to detect, they can actually prove in IP code that this IP belongs to me and not to the adversary. So therein comes the overproduction. Now again, once it goes to the foundry stage, it is also possible that somebody in the foundry, that is an adversary in the foundry, can launch reverse engineering attack from there. If there's reverse engineering from the foundry stage, he would try to get knowledge or hold of the actual design netlist, because if he gets hold of the actual design netlist, then he can also pirate the design. So therefore, encrypted design netlists needs to be performed or designed by the IP vendor and the associated vendor. So as you can see, there are different threat models, and for them there are different security measures in place.
Thank you, sir.
Okay, sir.
Is there any other question? So if no question is there, then I thanks Professor Anirban Sengupta for his nice experience, and he has just shown many case studies. Actually, it is actually his research, and I hope our participant has got many ideas which they can implement along with their PhD student. Thank you, sir. Thank you for your time.
Thank you, Dr. Swain, and thank you, Professor Mahapatra, once again for having me here. Thank you and all the very best.
Okay, so sir, we used to take a photo for participant. So as you are not having, we'll just have a, I request participant to kindly switch on their camera. Okay, I need to allow the camera. Okay, it is there. So you can just switch on camera for some time. Sir, can you just on-share your screen, sir? Okay, fine. Thank you, sir. Thank you. Okay, okay. Thank you all. Thank you all. Thank you, sir.
Thank you so much. Thank you and all the very best. Thank you.
Thank you, sir.